your biochemistry from A to Z. Remember, amino acids are amphiprotic, amphoteric, and zwitterionic, my favorite word. So what do all these terms mean? Amphiprotic. Amphi means both. Protic refers to protons. So an amphiprotic molecule is something that can both give and take protons. Amphoteric refers to its ability to act as an acid and a base. And so you might be thinking that these are the same thing, but amphoteric can be a bit broader because it also involves like Lewis acid bases, and I'll get into this, don't worry. My favorite, Zwitterionic, that refers to a molecule that has both positive and negatively charged parts, like fully charged parts, but the molecule is neutral overall. This is the case with amino acids, with free-floating amino acids, like in their like normal form, so like at bodily pH and stuff, because it's going to be pH dependent, as we'll see. But in the usual form, so although we traditionally draw them in their like anionic forms, amino acids really are in this like zwitterionic form most of the time, where the carboxylic acid group has already acted as an acid. It's already given up its proton to become carboxylate, which is negatively charged, anionic. But the amino acid is still neutral overall, because at the other end of the thing, at the end side of things, that amine group has already acted as a base, and it's taken a proton, and so now it is positively charged. And so you have a positive charge, a negative charge, neutral overall, boom, you've got a zwitterion, and a really, really cool word. So zwitterionic is not the same as polar. So basically, with the zwitterion, you have a separation of charges, but those are full charges. With polarity, what you're talking is about, it can be like that they have full charges, but typically you're talking about like partial charges. And so with like water, with the oxygen pulling electron density away from the hydrogens, the oxygen is partly negative, the hydrogen is partly positive, and the way they're aligned, you have a dipole where the oxygen, you have like an arrow, you could draw an arrow with the direction of the charge, and so we call it polar. But those are partial charges. And with the zwitterion, you specifically have like a negative charge and a positive charge. And it doesn't matter like if they're like in a line or whatever, that you have this great, but you have these full charges. So although the molecule is neutral overall, so although it has an equal number of protons and electrons, some of the atoms themselves are like assigned more or less protons or more or less electrons than they actually have. So the number of protons for an atom is fixed, depends on their element. The number of electrons can change. So if you have an unequal number of electrons, you have an ion. But if you, that's at like the atom level, but if you have like, with a molecule, if you have you can have an equal number of electrons and protons overall, which is the case with the zwitterion. But if you look at like the individual atom or whatever, it's going to have more electrons like assigned to it than it has protons. In that case, we would call it anionic. If it has fewer electrons assigned to it than it has protons, then it would be positively charged, cationic, because protons and electrons have equal but opposite charges. So we can refer to them as being ionic, like those atoms are like ionic, or those groups or whatever, but overall the molecule is neutral. The difference is with like, so with polarity, you don't have to have like a full charge. So it's just kind of like the electrons hang out more around the partly negative thing and less around the partly positive thing. But it's like the electrons that they're still like assigned the actual number of electrons that they actually have when we're talking about like polar bonds. We're talking about polar molecules, that takes into account like the whole directionality thing. So like that they're not like canceling out or like, yeah. So yeah, so Zwitter comes from like German for hybrid, so it's like a hybrid but of ion. So ion is charged things. And so you have this plus charge, this minus charge, neutral overall, and it's zwitterionic. To note that zwitterion is not like it's a molecular mood. I like to think of it as it's like pH dependent and then not on always state. So just like you have like qualities that you always are,
and you have qualities that you like, moods that you get in. And so maybe it's gloomy outside and you're in a gloomy mood, and it's all sunshiny and you're in a happy mood. Well, amino acids are like that, but in terms of charge. And
if you change the pH to go to some like extreme pHs and stuff, then you can get, if you go to acidic, so you have lots and lots of protons, we're talking low pH. In that case, the carboxylic group is going to protonate, and now you have the carboxylic acid group. And so now you still have that protonated amine group, because that protonated way before the carboxylate did. And so now that is going to have a +1 charge overall. Your amino acid is no longer a zwitterion. So what if you go to the other side of things? What if you go more basic? So you take away protons, you're raising the pH. Now you're taking away protons. So the carboxylate, well, it already didn't want it is going to lose that, like, it's already lost that once you've gone like past like pH of like 2. So it has a pKa of around 2 to 3. So that means that at anything at that like 2 to 3, it's going to be like half of it is going to be protonated, half deprotonated. As you start going away from that, you're going to get more and more in the deprotonated state. And so for every pH unit of 1, you're going to get 10 times more. So at a pH, if it had like a pKa of 2, at a pH of 3, like 10 times more is going to be deprotonated than protonated. So you're quickly getting away from any like part of it, like any little speck being protonated. So once you go past that point, now you're going to be deprotonated, and we don't need to worry about the carboxylic group. We're just going to say, okay, it's going to have a negative charge. What if we go on the other end, though? So we talked about the amino group being able to act as the neutral form, being able to act as a base and accept a proton, becoming a protonated and positively charged. So this is going to happen. It has a pKa of around 9 to 10. And when we're talking about the pKa, we're talking about the acid form. So we're talking about the ability of that protonated amine group to deprotonate and its readiness to do so. The pKa of 9 tells us that it's not going to, only half of it is going to be deprotonated at 9. And then like as you go higher and higher up, more and more of it will be deprotonated. But below 9, more and more will be protonated. So at our bodily pH of like 7.4, you're always all going to be protonated. And but if you go to an extremely basic condition, extremely alkaline, low proton availability, now there are fewer protons available, and so the amino group is going to give up its proton, become deprotonated. Now it is not negative, now it is not positively charged, it's not ionic, but the carboxylic group is still negatively charged. It is ionic, because remember, it's ionic when it doesn't have a proton. The amine group is ionic when it does have a proton. And so you still have this negative charge from the carboxylic group. So now you have a negatively charged amino acid. You are no longer a zwitterion. So in the center, though, you have that zwitterionic state, and this is going to be the predominant state most of the time because the carboxylic group, the carboxylic acid, has a pKa that's so low, like 2 to 3, and the amine group has a pH that's so high, like 9 to 10. And so in that middle, you're almost always going to have this zwitterionic form, so you can always use this really fun word to say, zwitterion.
So sometimes you actually have a third pKa for an amino acid, and that could be from like the side chain, because some of the amino acids can act as acids or bases. We're talking about lysine, arginine, histidine, aspartic acid, and glutamic acid. So more on that in other posts. But the reason why these are like approximate values, so it actually is, there's a range. Even if the side chain does not have its own R group, these pKa's for the backbone are actually going to have slightly different values depending on the amino acid. So you can look for yourself at like millipore sigma has an amino acid reference chart. coming from Lyde's Handbook of Chemistry and Physics, 72nd edition. But there's like a ton of different charts you can find. But basically, so they're showing you like the pKa1. So this is the carboxylic acid, and this is going to be the amine group. And so you can see that these are going to range from around 2 to, and these are going to somewhere around like, so you have some at like 1.82, some at 2.34, and with the amino group, you have some of these are down in the 8s, some are up in the 9s, some are even in the 10s. And so you can see that it's going to depend on the identity of that R group, even if the R group itself is like totally neutral or whatever, because it's going to be influencing the local environment and how willing it is to give and take and stuff.
So yeah. So most of the time you'll see them drawn though, like in their anionic form, which isn't really like, doesn't really exist or whatever. It's just like a convenient way to draw things, sort of thing. But so you might think, so the terms can get kind of confusing with acid versus base, but it's important to keep in mind that acid and base are just flip sides of the same coin. So when something gives up a proton, it becomes its conjugate. When something acts as an acid, gives up its proton, it becomes its conjugate base. Now this can take, the base can act as a base, take a proton, and become the conjugate acid again. So they're flip sides of the same coin. So we can only really talk about an acid or a base in whatever form it's in. So the carboxylic acid can act as an acid, donate a proton. Now it's a carboxylate, which is its conjugate base, but it's a really, really weak base, so it doesn't really want to take a proton. That's why you have to get it to such extreme pH, low pH, in order to get it to protonate, and when it protonates, then it's neutral. If we go to the amine side of things, it is acts as an acid when it has an extra proton. So when it's in its charged form, then it's acting as an acid. But when it's in its neutral form, it's acting as a base, picking up a proton to become the conjugate acid. And now, so in the Zwitterionic form, it's capable of acting as an acid. And in the Zwitterionic form, the carboxylate is capable of acting as a base. So it can get kind of confusing when you think about, oh, it's a carboxylic acid group. Well, it's already acted as a carboxylic acid. It's acted as an acid, and now it's its conjugate base, but it's a really poor base, so it's going to stay in that negatively charged group because it's really happy like it is. The amine group is going to act as a base, pick up a proton, and now in this Zwitterionic form, it can act as an acid because it picked up that proton, and now it can donate it to something else. So because it can act as both an acid and a base in this Zwitterionic form, as well as in the non-existent non-ionic form, I just wanted to tell you about it because you'll often see it like drawn and mentioned that way, and I don't want to confuse you further. But in those forms, it is amphoteric, which means it can be acting as both an acid and a base.
So basically, you can have this carboxylic group acting as a base and the amino group acting as an acid. And so sometimes it can get really confusing because you look and you read things and they're like, amino acids are amphoteric because they have the carboxylic acid that can act as an acid, and the amine group, which can act as a base. Except that for an amphoteric molecule to be amphoteric, it means that both of those are present in the same molecule, like at the same time type thing. And so only in like this Zwitterionic form and just like this non-realistic, non-ionic form, as we just seen from the pKa's, only in this like Zwitterion form are you amphoteric, where you have this ability to act as both an acid and a base, although it's kind of in the opposite way of what you might normally think of as being the acid and being the base, because acid and base are two sides of the same coin that depend on whether or not you've already given up your proton. So hopefully you won't get confused by that. But often we just talk about like amino acids as being amphoteric without really thinking about like whether the like what state it's in, because you can go back and forth between the acid and the base. But it's just important to note that it's this, you can see here, this is how you can see that can act as an amphoteric molecule, giving and taking protons.
It's also amphiprotic, which means that it can give and take protons. And so we've been talking about an acid as something that gives protons and a base is something that takes protons. But this is just one definition of an acid and base. This is the Bronsted-Lowry definition of an acid and a base. There's also this thing called the Lewis definition of an acid or a base. In that case, an acid is something that accepts a pair of electrons, and a base is something that donates a pair of electrons. All Bronsted-Lowry acids, so all of the proton givers are also Lewis acids. In that case, though, the proton, when you talk about that, you're losing the proton. So basically, you can think of the electrons being kept behind because you're losing the proton. So you are accepting a pair of electrons in a way. You're accepting the pair of electrons from that bond as you're giving up the protons. So all Bronsted-Lowry acids are Lewis acids, but not all Lewis acids are Bronsted-Lowry acids. And you see this a lot with metals, which can form like these dative or coordinate bonds. Basically, the metals, they have these big diffuse electron clouds, and they're usually positively charged, and so they don't really mind if a couple of electrons sneak in there, and so they can form these bonds where one molecule is donating a pair of electrons and just kind of like sneaking in there. And so you see this a lot with with some metal like hydroxides and oxides and stuff. They can act as these Lewis acids, but there's no protons involved. It's typically like an oxygen's lone pair of electrons that it's accepting to form this bond. And so there's no protons involved, so we can't call it a Bronsted-Lowry acid, but it's still acting as an acid. It's just a different kind of acid. It is a Lewis acid. And so those type of molecules, if it can act as both like a Lewis acid and a base, but not necessarily a Bronsted acid or a base, then we call these are still amphoteric, so they still can act as an acid and a base, but they're not amphiprotic because they're not acting as a Bronsted-Lowry acid and a base. All Bronsted-Lowry acids and bases are also Lewis acids and bases, but not all Lewis acids and bases are Bronsted-Lowry acids and bases. Bronsted-Lowry acids and bases are like a special case where where a proton is involved. So if something is accepting a proton, acting as a Bronsted-Lowry base, then it's donating a pair of electrons because the proton is coming in without electrons and it's donating it. If something is acting as a Bronsted-Lowry acid and giving up a proton, now it's basically accepting a pair of electrons because it's taking those electrons from its bond and ejecting the hydrogen as its proton, so without its electrons. So it's keeping the electrons from the hydrogen, so it is acting as a Lewis acid.
A few examples of things that might be amphiprotic versus amphoteric, and I should note that like most everywhere you'll just see amphoteric. You're not going to see amphiprotic, probably won't come up unless you're in, it could come up in like school or something, and that's why I wanted to mention it, because it kind of got confusing for me. But so here's some examples. So basically, if you say amphoteric, if something is like a proton giver and taker and you call it amphoteric, that is correct. So amphoteric is kind of like the safest thing to say because it encompasses all of this. And another thing is we call amphoteric molecules amphilites. And so basically here you can have some common examples are water. So water can act as both a proton acceptor and a proton donor. So here we're talking about amphiprotic molecules. And so remember, it's also amphoteric though. And so water, you can see this, this copy of water is acting as a proton acceptor. So it's acting as a base. This one is acting as a proton donor. It's acting as an acid. You can also sulfuric acid, so HSO4. In this form, it can act as a proton donor and become SO4 2 minus, or it can act as a proton acceptor and become H2SO4. And the so there are some, however, there are some amphoteric molecules that are not amphiprotic, and this goes back to the whole like Lewis acid base things that you might see with some metal oxides and hydroxides. And so an example of this is like aluminum hydroxide, so it can act as a proton acceptor, and this hydroxide becomes water, taking the protons. So this is okay. This is what we're used to with acids and bases, right? But then we go to its acid behavior. So if you react it with the base, now what can happen is that you can get these complexes where this OH is just kind of like latching on here. And so the oxygen, it's using a lone pair of electrons to kind of just sneak into the aluminum's electron cloud through this like coordinate bond, and you don't have any proton passing, but it's still acting as an acid because it's acting as a Lewis acid. But remember that amphoteric covers everything. We also can have a value called the PI, or the isoelectric point, which is going to be the point at which this is neutral, and it's going to be the average of the pKa's, so it'll be about 6. This doesn't mean that at like a pH of 7, you're still going to have it predominantly in the Zwitterion form. It's just that you have that like equal number of more and less positive at the isoelectric point. But you can think of the amino acids as basically always being in the Zwitterionic form, even though we often draw them by like convention and stuff as just in their unionic, so the non-protonated form of the amine group and the protonated form of the carboxylic group to be carboxylic acid. But they're typically actually in the Zwitterion form. But we can calculate for like the average or whatever, and then, but of course we have to remember that in a protein, these are all like linked up into a form of proton, and so when they join together, they're losing their amino and acid groups, and so they're joining together, and so now you only have one of these groups at each end. So if you're trying to calculate like the PI for like a whole protein, you have to only take into account those ends, but more importantly, all of the different R groups. And so it's not something that you would want to do with your pen and pencil, but there are programs like ProtParam that can help with this, determining like the isoelectric point for a protein, which can be really useful for like chromatography and isoelectric focusing. We call amphoteric molecules ampholates. And someplace you might see this with isoelectric focusing. So basically proteins, as we talked about, are all going to have like different combinations of amino acids, and so they'll have different isoelectric points. You can use this to separate proteins based on their isoelectric points if you travel them through a pH gradient. And so you can use a solution of ampholytes, so a solution of molecules that can exist in these various charged states. And when you send it, that traveling through like an electricity, then the electric gradient, then the ampholytes will kind of order themselves based on their isoelectric points, and that'll create this pH gradient. And then you can send your protein traveling through it, and then the proteins are going to travel through to the other, like if you put a protein like between two, like a positive charge and a negative charge or whatever, it'll move towards the charge that's opposite of it, because like opposite charges attract. But as it goes, it's going to be picking up or losing protons. And so this is going to make it less charged and thus have less of a drive to move towards that electrode. And so it'll stop. And often this is used as like in part of a 2D electrophoresis. So you do this isoelectric focusing point step, and then you take like the strip and you stick it on top of like just like a normal SDS page gel and run it to separate by size. And that gives you better separation, which could be good if you have like a very complex mixture.